Thank you so much. Thanks. Thanks, Uri, for that kind introduction. So, yes, there was a few years when my students and I did a lot of attacks, and since then we've been making up for it by doing proofs. So we are on the positive side of things. So today I'm going to be talking a little bit about what role formal methods and formal verification can play and is playing in the design and implementation of crypto protocols, and so on. This is joint work with a ton of people, so I'm not even going to try to mention them all. So sometimes it feels like we're going through like the golden age of crypto, right? Because every year, I mean, you would imagine that this wouldn't be the case, but every year there's so many new crypto constructions which are being designed, standardized, implemented, deployed. There are new protocols that are coming through. There's even new exciting applications that gets everybody excited about things. And these are really kind of making the field feel very dynamic and exciting right now. But despite all this excitement, we still haven't solved the problem of how to securely design protocols, how to securely implement them, and so on. So yesterday, you talked a little bit about Threema, and I really encourage you to go read this paper, not because it's absolutely current or so on, but it gives you lots of interesting ideas about what goes wrong even today in fairly classic designs, right? And if you go look at the paper, this is by Kenny and his group, the title is 3 lessons. So let's look at the 3 lessons. It's got 9 attacks in it, and we can argue about whether the attacks are relevant or realistic or not. But the lessons I kind of like. So the 3 lessons, the first one is, don't roll your own crypto protocol. So one way of interpreting this is that if you're trying to do something for which there already exists some well-known, well-analyzed, popular, or standardized protocol, why don't you use that? Under the assumption that this well-known protocol maybe has seen some analysis, people have tried to break it, and if it's still standing, perhaps you can have more confidence in it than something you would do by yourself. But there is the acknowledgement that almost any application doesn't use just one construction or one protocol. Inevitably, if you want a full-featured application, you'll have 2 or 3 protocols you'll have to compose. So the moment you do that, you have to worry about their composition, cross-protocol interactions, and so on. So they say, beware of cross-protocol interactions. So accepting the fact that you are going to roll up not the whole protocol, but some aspects of it, some composition, some layering, the third lesson from Threema that they quote is that formally analyze the protocol design. They call it be proactive, not reactive. So try to analyze your design before you implement and deploy it. Okay? And this is, of course, because they are cryptographers, they like to do this stuff. I'm going to extend this a bit more, which they don't say in their paper. And I think that you should formally analyze your design using some kind of automated, semi-automated, mechanized verification tool. And the reason is that your protocol, even though it may be taken from the standard, it might have analyzed it completely with a crypto proof, is never going to sit still. It's going to change. You're going to have version 2, version 1.1, you're going to have an extension. Something's going to change. You're in the field of innovation like Threema, you're going to change it every 2 years. And when you change it, are you going to restart the proof from scratch? Or can you rely on some existing artifact that you can mechanically check, and you can modify the proof, and you can mechanically check that it still works? I think there's a lot more percentage if you can actually invest in this. So that's going to be kind of my focus. So let's take that lesson and say, well, what does it look like when you try to do formal analysis of your protocol in the design phase already, whether you're doing a construction or a protocol or whatever? The best example of this, of course, is what you call a TLS 1.3 experiment. So between 2014 and 2018, there were a bunch of groups, including groups here in the University of Ruhr, who kind of contributed to the design and analysis and attacks on TLS 1.3 before it was even standardized. So they were analyzing early draft versions of the standard. And these were like all kinds of analysis. There were cryptographic attacks and proofs. There were mechanized proofs, which they were done using the tool called Cryptographic. There was symbolic analysis done with verification tools like Tamarin and Cryptographic. There was even some verified implementation work. Okay, so there was a comprehensive set of results, a lot of pen and paper proofs, and some mechanized verification proofs, all contributing towards some confidence we could have in the protocol before it was even published as a standard. And this effort continues now. Even now, you will see 1 or 2 more papers because the TLS protocol continues to have extensions. So for example, this year we published this paper on the symbolic analysis of privacy for TLS 1.3 with the encrypted client hello extension. So I'm not going to talk more about that paper. I'm just saying that there's more work that keeps coming. And here, what we were able to do was to take the proofs that were already done in 2017 using ProVerif And we added the encrypted client hello extension, and now we proved a whole set of new properties about the protocol, which are privacy properties. But we were able to build on an existing mechanized proof and extend it. We didn't have to go back and do everything from scratch. But that's enough about TLS. That's old news. Let's go back to the kinds of questions that Jörg was asking yesterday. You just want to encrypt a message. This is what Threema wants to do, right? Just encrypt one message, right? It's from one person to another. And in order to do this, you say, well, how do you do this? You know the public key of the recipient. It should be fairly easy, right? So at least for a symmetric key, we know we can encrypt a symmetric key with a PS public key. We can use a HPKE, public key encryption, or a CHEM. We can use RSA if you really want, or we can use ECIES or post-quantum CHEM, whatever we want. But of course, that's not what you normally do, right? You have got other questions, which is, well, I actually want to encrypt a long message. Or sometimes I want to encrypt a stream of messages. Sometimes I want to authenticate the sender, and sometimes I don't care about authenticating the sender. Sometimes I want to authenticate or have some integrity for the encryption context. I want to add some associated data to the key that I'm deriving, and sometimes I do not. So there's a lot of use cases, and this is, in fact, the reason why protocols like Threema are rolling their own public key encryption, actually a hybrid public key encryption scheme, because they need some of these features which are not there in existing construction. So what you need is something really flexible, but the moment you try to add on things to these constructions, often you get it wrong. There's an attack, and this is one of the attacks that was in Threema as well. So in response to this sort of need, in some sense, and despite the rule that you shouldn't add the 13th standard when 12 standards don't suffice, we did publish this RFC last year called HPKE, along with my students and student Benjamin Lip and other people. And the idea behind HPKE was to actually define an agile and modular construction for hybrid public key encryption, where you take any CHEM, any KDF, any AAD, and you show how you can put them together in a way that is sort of modular, secure, and so on. And underneath it, you could implement the CHEM in any way you want. So for example, right now, the main cipher suite uses the NIST P curve or X25519 for the CHEM, and so on, or there are multiple AEDs. But tomorrow you can imagine extending this with a PQ CHEM. That should be fairly straightforward. But how do you know you didn't get this wrong? And this is where the value of the standardization comes in. What's in the standard? There's nothing technically new. There's nothing, there'll be no aha moment for you. It's very classic stuff that any of you would normally do, right? But what you want to make sure is that it's done once and for all, in a way that's interoperable, in a way that's standardized, and in a way that we can prove correct. So there's a paper by these authors on analyzing the standard, and this came out basically concurrently with the standard being published. So this is the kind of example of where you do the design and the analysis, and you publish them together. But let's go one step further. How do you encrypt a message to a whole group of people? Well, you can say you know how to do HPKE. Let's just do HPKE to all N participants. Well, you can do slightly better, right? I mean, this is what signal sender keys does, is that you generate a key, you CHEM it to all the M participants, and then after that, you use this key to encrypt every message, and you sign the message as well. But what this means is that every time the key changes, like if you want to remove one person from the group, you're going to effectively have to do an order N computation, which means order N public key encryptions every time you want to change the key. So adding is easy, but removing and updating a key is pretty hard. So in response to that, there's this proposal called TreeChem, which came up in 2018. And the idea was that instead of just saying there's a flat structure and you have to encrypt the key K to all N participants, let's create a tree of subgroups and try to maintain key for every subtree, a public key, private key pair for every subtree in this subgroup. And we'll use this tree of subgroups to somehow efficiently send messages to each other, but also efficiently update these keys. So that's the key point. The updating should be cheaper than order N. Because in the kinds of protocols you're looking at, we want post-compromise security, which means you want to do things like the double ratchet, which means that you want to keep updating keys. Also, you might want to remove people from groups, and all of these features require you to update keys. Just to see why this is more efficient, let's just take one example. This is a tree with 5 users in it, A, B, C, D, and E. The other leaves are empty, okay? So the users are represented by the leaves of the tree. And then the nodes represent subgroups of them. So the node above A and B is a subgroup consisting just of A and B. The node above that is a subgroup consisting of A, B, and C, and so on. So what the protocol does is that maintains private-public key pairs for every node in the tree. The leaves themselves have their own public-private key pair, but that's like the long-term private-public key pair that they have. But they can also update this over time. They start with their long-term key, and then they update it over time. So suppose B here wants to update his public key from PKB to PK prime, okay, PKB prime. And of course, the private key as well. So what he has to do is that he has to now, since he's changing the public key, his own public key, he doesn't want anybody who knows the old private key to be able to decrypt any of the keys on that path, SAB, SABC, and SABCDE. So he wants to invalidate the entire path of keys from that leaf to the node, to the root, replace them with fresh keys. Okay, so this is what he does. He sends an update which says, I'm changing my key to PK prime, my parent's key to PK prime AB, and so on, all the way to the root. So he's changing log n keys, and he has to convey these log n keys to the peers, the co-path in the tree, because they will then be able to decrypt it and update the keys, the public keys that they have for the keys that they know for the root. So using about log n ciphertext, you can update the keys in this tree. And that's basically the key element here. If you didn't get all full details, just imagine trees go to log n. That's the right intuition, okay? So adding people to the tree is still order 1. Removing and update are log n operations in computation and in the size of the message that you have to send. And that's that is the heart of the idea of this standard called messaging layer security, which is now on draft 20 and supposed to be published any day, like in the coming weeks. And if you want to understand messaging layer security, it's a pretty big standard, but we'd like to think of it in terms of 3 components, right? So there are 3 components to it. One which we call tree sync, which is you have this tree, right? Everybody now is going to do these trees of key stuff. And we have to synchronize this tree across every member of the group. So there's one sub-protocol, which on all 3 sub-protocols run in parallel, whose only job is to synchronize the trees and make sure everybody has the same state. Then once everybody has the same tree, the next step is how do you derive a key for all the subgroups in the tree. So given the public keys in the tree, we can do this key derivation, encapsulate trees, decapsulate fresh keys, and so on. And that's the tree chem aspect. Its job is to make sure people have shared group keys. And once you have the shared group key, then we come to the tree dem, which is a protocol for doing encryption of application messages. So those are the 3 components which basically run in MLS. Most of the attention has been given to the middle part, tree chem, but I think, in fact, tree sync might be even more important. Because the goal of tree sync here is now to give authentication and integrity for the state, for the shared group state. And to do this, it uses signatures and a tree hashing mechanism, actually 2 tree hashing mechanisms to do that. Okay? But it doesn't care about secrecy, confidentiality. The tree is a completely public value, okay? It's almost, I shudder to say the word blockchain, but it's like a public value that everybody has to agree on. Tree chem, on the other hand, is the one that is going to actually establish secret keys. So you want forward secrecy, you want post-compromise security for the keys. It's doing your ratcheting, and everything is happening inside tree chem. To do that, it's using a combination of HPKE and a key derivation function. And the tree dem part, it doesn't care about any of the key establishment. It has a key. Now it's only going to encrypt application messages. But even there, you have to be a bit careful. Now you're in a group. So if somebody sends you a message in the group, you want to know, A, whether they are in the group or not in the group. Okay, that's easy. But then you may also want to know which person in the group sent you a message, especially if you really want some proof that this message was sent by somebody in the group, and which person it was. So it has sender authentication and forward secrecy as well. So it does a ratcheting as well on the keys for forward secrecy, and it does sender authentication using signatures. So these are the 3 components. That's all I'm going to say about it. And they can be analyzed independently. So for example, this year we published a paper just on the tree sync component, making minimal assumptions on the other components, and said, even if tree chem is pretty much completely broken, and even if tree dem is completely broken, except that it has to use signatures in this one specific way, we can prove that tree sync is secure. And I believe that you can do the same proofs for the other paths, and that work is ongoing. But ours is not just the only analysis. There's a whole bunch of pen and paper proofs at all the crypto conferences that you might know of of various versions of MLS and drafts of MLS. And this is a table from Alvan et al.'s paper at Crypto 2022. There's a few more papers that have come out since then. All right, so that part was about how do you analyze designs of protocols before you deploy and implement them. But at some point, you're going to have to implement them, right? So how do you make sure that your implementations themselves don't break the security that you've so carefully proved about your design? Because in fact, like we saw in Threema, or if you go look at them, a bunch of the problems are actually in the implementation, not in the design. A bunch of them are in the design, and those are worse, obviously, because those problems will exist in all the implementations. So if you want to implement something like Threema, you're going to need some crypto, right? And naturally, depending on what kind of environment we are in, there's a bunch of crypto libraries we can go and get crypto from, okay? And many of them are built into the operating system, but other ones which have high reputation or just easy to use and so on in the language of your choice. But every year, there are bugs in these. So do you really want to put the entire crypto library, which is like OpenSSL or Linux crypto, into your trusted computing base? Maybe you're OK with that for the design, for the case you're in, but perhaps you can do better. But before that, let's just make sure that we understand what kind of bugs there are and whether these are actually real bugs. So some of you may have seen this. This is the psychic signatures bug in Java last year. Psychic actually makes it sound much more sophisticated than it is. It's actually an extremely stupid bug. It's an ECDSA signatures. So in ECDSA signatures, when you receive an R and an S, the first thing you check is that R and S are not 0. Otherwise, it's trivial. The equation just works out instantly. So it's the first thing everybody does, and everybody should do. But Java, for the last 3 versions of Java, actually was not doing that check. Instantly, what it meant that anybody could send you a signature, and you would accept it, basically. So it was like unbounded forgery of signatures was possible if anybody was using ECDSA. So this is an extremely stupid bug. There are many other bugs, in fact, in Java and in other libraries, which are a bit more sophisticated, okay? Which are harder to find. The good news is that you don't have to use libraries for which you have to trust that they didn't make this kind of a mistake, because there are a lot of verified crypto libraries now available. It's been a big topic of research for the last 6-7 years, and now there's like libraries in C, Intel, Assembly, Rust, Go, which are formally verified. They tend to be separated by the tools that they use to do the verification. Some use F-star, some use EasyCrypt, some use Coq, and some use some SMT solvers and so on. But on the whole, they produce code, like C or assembly code, that you can just take and you can use in your application. So the good news is that for almost any crypto algorithm, any classical crypto algorithm that you need, you shouldn't be going on GitHub or whatever, and or on Cargo and just downloading a crate, which you don't know who's written, whether it's got bugs in it or not. There probably is a formally verified implementation of that primitive somewhere by some reputed group that you can use. The bad news is that they are researchers, so the code is research-level code, which means it's provably correct, it's very efficient, but the APIs it might expose might be lower-level APIs than you would get from like the Go crypto library, for example. And the formal verification that they are doing is, again, some specification. So if you want to read the specification to understand what actually has been verified, what the preconditions are, and so on, those are probably written in a language that will be quite unfamiliar to the cryptographer or the crypto developer. So to understand this issue a bit more and what our proposal for solving it is, let's just consider what the workflow of verifying a crypto algorithm is. Now, verifying a crypto protocol is a bit different, but it fundamentally has the same shape, okay? So to do this, of course, you always start from the standard or the spec. If it's like a NIST PQC candidate, probably the spec that they were submitted to the NIST. So here is the CHA-20 RFC. You go inside it, you'll find some pseudocode, some English language description of what it's supposed to do. And you carefully read this, and you understand it. There's also some test vectors. And then you write a formal spec. So you can write a formal spec in a language like F-star or Coq on top, which is a fully functional language, something like Haskell and OCaml. Or you can write the formal spec in a language like EasyCrypt, which is a bit more like a while language. It has while loops and mutable variables, but it still actually has a formal semantics, and it's a very small language. But OK, you can basically transcribe it. And once you have transcribed it, well, the thing that you really want is the implementation. So in the HACL star project, what you do is you take the standard and you implement it in a language called F star, but actually it's a subset of F star called low star. It's a C-like language. And then you can compile that code to C, OK? Or you can write that code in this language called Jasmine, which is the one on top. And if you write it in Jasmine, you can compile it to Intel assembly, and maybe some other assemblies in the future, but right now, Intel assembly. And so these implementations will use all the optimization tricks that crypto developers use. It'll use SIMD crypto, it'll try to reorder instructions, it'll do all the things that can maximize the performance, because that's what you need from a lot of these crypto algorithms. So the final code that you have is going to look quite different from the formal spec that you wrote. So obviously the next step, and this is the verification step, is that you take your formal spec and you take your implementation and you prove that they match, which means that there is no memory safety bug in the low-level code, that it's functionally correct, and in some cases you also prove the absence of certain kinds of side channel vulnerabilities. But I must say that's like the least sophisticated part here, and there's not very good answers that we have for side channels right now in many of these tools. So coming back to the good news, there's always an implementation for any algorithm. You want SHA-3, you want AES, you want, I don't know, Kyber even. There is a verified implementation. So don't roll your own crypto. You can use one of these. So you don't have to sacrifice performance. A lot of the implementations which are formally verified are as fast as, and in some cases faster than unverified crypto. So there's no sacrifice of performance. The proofs are all mechanized, which means that you can run and rerun them yourself. And if you may want to make some cosmetic change because in your company you like to use a certain variable naming convention, you can make the cosmetic change and rerun the verification just to make sure you didn't screw something up. Okay? And for the most part, you don't have to read or understand the proofs or the code. You can just kind of use it as a black box. Okay? The bad news is that since you don't want to look inside the code because it's auto-generated or formally verified code or code written for verification, it might be hard for you to extend or use or combine code from different libraries in a nice way. And if you really want to understand what has been verified and whether you are using the verified code correctly, you have to look at the specs. And the specs themselves are typically written in a tool-oriented formal language, like Coq or EasyCrypt or FStar. So even though the code finally that comes out is C or assembly, the spec is still in one of these languages, which you have to read in order to understand what the code is actually doing. And this is important because sometimes there are subtle preconditions in the code. So if you didn't realize this, you just get some C code, you could call it with the wrong inputs, and in fact, even though the code was verified, because you broke some precondition, you would crash. So to address this, we are kind of developing, along with a bunch of tool developers, this shared language called HACspec. And the idea of HACspec is to be a tool-independent spec language that anybody who's familiar with crypto algorithms and crypto development should be able to read and even write. It should use familiar languages and tools, and should enable us to write code or specs for crypto algorithms and protocols as well, which look kind of like pseudocode. It should look like pseudocode, but at the same time, we want it to be executable so that we can test it. We can make sure that we can test it and understand that it's doing the thing that we expect to do. For small algorithms, small constructions, testing may not be necessary. You just look at it and you say, yeah, I know this is exactly what the NIST is asking me to do. But as these things get bigger and bigger, and then more newer algorithms are actually quite big, you actually do want to test it and make sure that you can run the test vectors, even generate test vectors from it. But of course, the main goal here is that whatever spec you write in this language, you should be able to translate to the formal languages like FStar, Coq, EasyCrypt, whatever it is that you need to do, the proofs that you actually are going to do. So the language you come up with, HACspec, is a subset of Rust. But it's a very small subset of Rust. It's purely functional Rust. In safe Rust, no external side effects, no mutable borrows, and all values are copyable. So if you're a Rust programmer, it'll be kind of familiar in a certain way, but also non-idiomatic, because you're never doing and mute ever. Okay? And because of that, that's what makes this like a predictable spec language. But on the other hand, you can just use your standard Rust tools, standard Rust development environment. And you get a library that provides a bunch of useful abstractions. For example, arbitrary precision integers, vectors, matrices, and so on. And we'll look at some examples of that. So what does it look like? Here's the first example. On the left is the inner block function from ChaCha20. That's the pseudocode in the RFC. And on the right is the HACspec code or spec for this. It's Rust, as you can see. But although on the left, the RFC code actually modifies state in place from the beginning to the end. So it's actually modifying the input state. On the right, it's not modifying the state. It's taking the state as input and giving out a new state as output. However, in the body of the function, you are allowed to locally mutate the state. That's OK, because it's a local mutation. Ooh, interesting. Wonderful. You guys can check every time an email comes in, looks like. I'm using Google Slides, so yeah, whatever. But on the whole, this is what you call state passing style. So it's just sort of passing around the state. So it's still purely functional from the viewpoint of anybody who's calling this function. There's no external side effects. Here's a second example. This is from the Poly 1305 spec also, which is also in the same RFC. And Poly 1305 Mac, if you look at the core construction, what it does, it takes a 128-bit string as a block. It converts it into an integer. That's what the first line is doing. Then it takes the accumulator, and it adds the number to the accumulator. Then it multiplies that with R. And all of the addition and multiplication is happening modulo a prime. And the prime happens to be a 130-bit prime, which is 2 to the 130 minus 5. And there are other specs where you use larger primes, 521-bit prime, for example. It's very, very common, this kind of computation. Now, when you're implementing this, you can't use 130-bit numbers. So normally, you would break it up into 32, 32, 32, 32, or 64, 64, 64-bit numbers, and then do some big num calculation or whatever. But in HACspec, you don't have to do any of that, because HACspec gives you a library with arbitrary precision integers which are represented by user-defined fields. So the user can define a field and say, this is a field modulo this prime, and then can just do arithmetic on this field without worrying about any allocations or freeing or any borrowing or anything. It just looks, for all purposes, for the user, it feels like the arbitrary precision integers are like native to the language, which of course it's not. It's all hidden under a library. So that's the spec in HACspec for it. The third feature in HACspec, which is of interest but also sometimes controversial, is that we allow you to mark what is secret and what is public. Because in a spec, actually, it's not so important, what is secret. It's just mathematics, right? A spec is just a mathematical object. But a spec is also a guide for the implementation. At some point, somebody is going to look at your spec, which is Rust. So they may even cut and paste it. But even if they look at the implementation and then they write their thing, they're going to use this spec as a guide. And they use the RFC as a guide, and so they're going to use your spec as a guide. So if you could mark, OK, these are the integers I'm assuming, or these are the arrays I'm assuming are secret, and these are the arrays I'm assuming are public, that's actually very good documentation for the user, for the implementer. Not just that, it might also help you point out the places where you have to be careful. So for example, the way this happens in HACspec is that for every machine integer, like U8, U32, and so on, there is a secret version, like capital U8, capital U32, and so on, which provides the same interface. You can do the same operations as you can do on regular machine integers, except with some restrictions. So you cannot do like division, comparison, and you cannot use those integers. You cannot convert them into array indexes, which means that it enforces a constant time style discipline. We call it a secret independence discipline on the specs. And the point of that is that you can quickly check in your spec, is there some place where I'm actually depending on the secret, doing some operation which is secret dependent, and that'll just give a little bit of a warning to the developer saying, hey, you've got to be a bit careful here. So for example, in the ChaCha20 spec, it makes no difference whether you use a secret integer or public integer, the code looks the same. Whereas in AES, the place where you access the S box, you'll say, if I have a secret integer here, which you do, and I'm trying to use that as an index into the array, the Rust type checker will say, sorry, there is no such method on this secret integer, so you cannot do this. So you'll have to explicitly declassify it before you use it, even in the spec. Now, this pollutes the spec, for sure. This is not a mathematical spec anymore. You're doing some declassification in your spec. So for some people, this may be like not tasteful enough, so they would just not do this. They would just use public integers everywhere. But if you want to use the spec as a guide to the implementer, that's not a bad thing to do. So you say, when accessing the S box, be careful, because in the spec, if you use secret integers, you have to do a declassify there. So you have to do something has to be thought through here in the implementation. And of course, what you can do is you can press a button, and from HackSpec, you can get out F star, Coq, and EasyCrypt. In the future, maybe more languages. So not all of these translations are perfectly working, but they work for this example, and a few more. And hopefully they will, because there are 3 different teams. One team in Aarhus, which is doing the Coq backend, the team in India is doing the F-star backend, and the EasyCrypt team is doing the EasyCrypt backend. So they're all at different stages, but the idea is that everybody commits to using the same original spec, and they all generate local specs from there. So how is this supposed to work? The idea is, if you're writing an application, we encourage you to write it in Rust. And in that application, you identify all the crypto that you need. Hopefully, it's all standard crypto, in which case you just call into the appropriate standard crypto. But if not, you write your crypto spec in HackSpec first. You write it down what you need in HackSpec. Once you've done that, you can test it already. Yeah, you can test it. It's like a prototype. You can already run it. You can do all kinds of testing. And once you're happy that you've actually got your application the way you want it, you can take your spec, you can translate it to Coq or EasyCrypt or F-star, whatever is your favorite language. Then you write your optimized implementation of whatever crypto that you specify. You verify it against the spec that you generated. And then once you've done that, you rewrap the optimized implementation with a Rust API, which is the exact same Rust API as the HackSpec was providing, so that your application can just move over from using the HackSpec prototype version to the optimized verified version. So it's like a seamless part of your development workflow. We're already doing this in a few examples, and to kind of show off how this works, we have a library, which we've also released, called libcrux. It's a Rust library, which combines a bunch of verified crypto under one roof. So the architecture is that at the bottom you see it uses HACL star, Veil, and libjade. It also uses AU curse, which is already written in Rust. And on top of that, it provides this layer, which has some safe APIs. It has HackSpec specs for all the crypto that it uses. It also documents how to reproduce the proofs for all the code that is underneath it. Okay? And each of these proofs is in a different system, right? So some of them are in Coq, some of them are in EasyCrypt, some of them are in F-star, but there is documentation on how you can reproduce this. And that's a discipline we want for this library. Anybody who has a verified implementation can submit it, along with a reproducible whatever recipe and some documentation. We will carefully look at the documentation, the specs. We will use HackSpec specs to match them with it. We will provide safe APIs and so on. So what do we mean by safe APIs? Well, even though HACL star is fully verified, when you generate the C code, the code basically produces an interface like this. This is for Chachapoly. So here there is a uint 8 star for the key, nonce, but we know that the key has to have 32 bytes. And the nonce has to have, let's say, 12 bytes in this case. There could be other versions. The MAC has to have a certain length as well. And we know that the cipher and the MAC have to be disjoint, actually. Otherwise, it won't work. The HACL star code won't work. Okay, so if you did not follow those, which is not there in the API, if you use this API incorrectly, your code will actually seg fault in certain cases. So you would be surprised. It's a formally verified code. I'm calling it, and it's seg faulting, which will be very weird. And the reason is, if you go look inside the HACL API, the F-star API, of course, there are preconditions that describe all of these things. So it says that the key has to be 32 bytes, a nonce has to be 12 bytes, a tag is going to be 16 bytes. And there has preconditions that say the key and the output have to be disjoint, the nonce and the output have to be disjoint, and so on. So you can't have these be the same arrays. It's interesting that the input-output, there's a constraint that says that the input plain text and the output ciphertext either have to be the exact same buffer or completely disjoint. They can't be like intersecting like weirdly. You have to be like, you can either do completely in place or completely disjoint, but you cannot do it otherwise. But all of this detail is there in the HACL star. API. And of course, it's also going to be there in the Jasmine and the Coq and everything. It's going to be there, but it's going to be written in that language, right? So it's how do you reflect it back in the way that is safe for the user to use. In Rust, you can do some of this, right? So that's what we do in the libcrux API. Some of the stuff we put straight into the types. So the lengths of arrays are straight in the types. The disjointness of arrays can be represented using the Rust borrowing semantics. Sometimes, some of these preconditions you can't represent as types, in which case you put in dynamic checks in the code of these Rust APIs that check those things, and if they fail, it gives a reasonable error rather than seg faulting underneath. And this is important because we are wrapping around assembly code and C code and so on. So we have to be careful about how to compose these things. So libcrux includes all of these algorithms. So some of them are taken from Whale, some from HACL, some from libjade, some from AU curves. So it's pretty comprehensive, but needs many more algorithms that we are continuously trying to add to it. And the performance is very good. So for example, on Intel machines, if you want to do X25519, you can use the HACL star and Whale combined version, which is faster than anything else out there, including OpenSSL. If you want to use SHA-3, you can use the libjade version, which is as fast as anything else out there, which is an Intel assembly. If you're on a Mac and you have an ARM M1 Mac, in that case, you can only use the portable C versions right now, because we don't have ARM assembly verified implementations at this moment. But you can see the performance is actually pretty darn good. There's no issue. It's faster, if not as fast, as anything else that you would be able to find. And that's not just it. Now that you have all of these algorithms in libcrux, you can now build constructions on top, like HPKE. So we have built an implementation of HPKE that underneath it uses all the algorithms from libcrux, and the implementation of HPKE is in HACspec itself. Okay? So you don't have to re-verify it. It's really compact and succinct. So towards conclusions, there's a lot of ongoing work on this. I've just shown you a snapshot of where we are going for HACspec and for the other tools around it. We want to put in a whole bunch of other backends, and people are interested in this, working on these subjects. So I think of this as more like a big tent where any verification tool, any verified library should be able to come in and plug it in, as long as it meets certain goals and as long as it works for Rust. All right, to conclude, I believe that protocol verification tools are now available and should be applied to protocols like, if you really need to design your own protocol like Threema, you can apply a verification tool to it and get pretty strong guarantees and find the attacks that people have found. And there are many case studies that you can use as a guideline. If you want fast verified code for your crypto algorithms, there's a ton of this stuff around, not just in my group. Many of this stuff is from other groups. And you can download and use. And in fact, if you really don't want to deal with it, you can use libcrux, which actually already combines a bunch of these things. And we encourage you to try out HACspec and libcrux. They're available. They're still kind of researchy, so they'll have lots of issues that you'll find and you'll report, but we encourage you to take a look at it. Well, thanks. I'm going to leave these for the slides. And just the last advertisement, because this is a project that is ongoing. We are really looking forward to hiring R&D engineers, both at INRIA and Crispin, to do these kinds of things that I've talked about. So if you have any students or you want to talk, just get in touch. Thank you.